So the next keynote. About 25 or so years ago, I was doing this thing called architecture, and I wasn't doing that well. It didn't quite gel with me. And this guy came over and said, "Oh, have you thought about building science? You know, we kind of teach them all in parallel, and you know, you could give it a crack, see how you go." And I did. He was quite convincing as well. And then I actually quite liked it, and luckily my grades started going up, so obviously that worked. And then I moved into career as a building scientist, so that was really awesome. Got through, I actually met my wife at architecture school as well, so that was awesome. He was also so convincing that he said, "Oh, there's this thing called IBIPSA, some website, something I've got to manage. Can you just sort that out for me?" And I was like, "Yeah, sure, no problem." Here I am still managing that website. It led to a lifelong career, a lifelong friendship with Mike. And who is he? Well, he's a building performance simulationist, and he's got, I looked it up, it said over 30 years of experience, but he's been doing this since I was born, like actually practicing since I was born, and I'm oldish. He's director for the Centre for Building Performance Research at Victoria University of Wellington in New Zealand. He's also an architectural aerodynamics advisor to the Wellington City Council, and he's been lecturing, as I said, since I was born. I'd like to invite Dr. Mike Donn to the stage and share his thoughts on useful lives. Mike.
I really don't need to be reminded how old I am, but there we go. I'd like to begin in the way that Quentin did today with an acknowledgement of the traditional owners and custodians of the land on which we stand and meet today. I was at a art gallery presentation by a local Indigenous person from a mob, that's how she described the tribes of Australia, to the north of here, who added something to this acknowledgement where I found, coming from New Zealand, fascinating. Because in addition to acknowledging the land of the Turrbal and Jagera people, she pointed out that they never ceded sovereignty, which is a really interesting question when you come from New Zealand as well. So I'd like to acknowledge the elders past and present, as well as emerging leaders. I extend that respect to any Aboriginal and Torres Island people also here today. And I'd like to move from that to an acknowledgement of where I come from. Now you can tell I don't probably have any Indigenous Maori background coming from New Zealand, but the traditional pepeha that we use and are trying to get better at using acknowledges who we are and where we come from. So tēnā koutou, tātou katoa, tātou being all of you, ko Puneke te moana, ko Nelson te waka, ko building science te iwi, ko Michael Donn tōku ingoa, Norera tēnā koutou, tēnā koutou, tēnā koutou katoa. But there's more. There was a second slide, but I will. No. Did you just change something? It doesn't matter. I will go on to the next slide. There was a second half to that pepeha, but essentially what we're doing is acknowledging there's a land that we come from. When I come to the iwi, the tribe that I come from, it seems to me that since 1993, when I first started presenting at these conferences, you're the tribe that I come from. Yesterday, PC gave a presentation on the history of neighbours, which I called him out on, and he said I should add something to my presentation. So in fact, I've got 20 minutes. I'm going to take a little bit of a moment to actually do that. Neighbours started, according to this 1999 paper by Alan Pearce from the New South Wales government, with an exercise that the Building Research Association of New Zealand contracted to lead, They were the people who developed, I know there was a question yesterday, where did the historic data come from? Well, they were the people who were experts in collecting historic data. And it was a colleague of mine, someone who I'm sure Quentin is quite familiar with, and probably Nikki and other people in the room, Nigel Isaacs, who led the team that employed Paul Bannister's firm to do the energy analysis, to do the simulation. So, admitting the chip on my shoulder as the junior cousin from across the sea, we feel that we had a little bit of a role in starting Neighbours. You've taken it far farther than we ever thought, and I have to admit, we've never had a politician brave enough to do what your politicians did, and we somewhat regret that because Neighbours New Zealand is still a voluntary process. So, I titled somewhat bravely this as All Models Are Wrong. And then I discovered that that was stolen by a colleague in the Education Forum yesterday. But I'd like to acknowledge that in starting with this, all models are wrong, there's another acknowledgement I need to make, and that is to all the people who have gone before us. I was going to acknowledge a number of people in this room, but in fact there's not just the people who are no longer here, the Joe Clarks of this world who aren't at the meeting any longer, the Laurie McElroys who aren't at this meeting any longer, possibly due to distance, I'm not sure, but we stand on their shoulders, and they are the people who fed my fetish. And my fetish is quality assurance in simulation, and that's why we're here today, and why I am proposing that in addition to acknowledge my fetish, we also need to go back to what George Box really meant when he talked about all models are wrong. Because I believe that, and this is where I want to have as much time at the end to actually have you debate with me, that the performance gap is a crock. The performance gap is something we should be ignoring if we're talking about building codes. Because the performance gap is somehow dependent on us letting the people who write codes believe that a model that is somehow a simulation, a reduction of the reality, can predict the future. If we take the model and create a calculation that can be used for compliance, and we let people believe it's a prediction of the future, then we're letting people misunderstand what we're doing. I would note that the second half of that aphorism, all models are wrong, it's just some are useful, isn't something that George Box wrote in 1976. He added it in a later paper in 1979. But in the 1976 paper, he had something that I think is far more interesting. And that is, we should be using our models, and we should be using them in building codes to look for the tigers, not the mice. If we're doing 8,760 calculations, you're going to hear me saying that number a lot, and I've heard it a lot in the last 2 days, then why on earth do we present that as one number at the end? We're not using the power of the tool, and we're not helping building code officials to use the power of the tool in any way that uses that density of information. It's frustrated me since 1993, when I presented a paper in this conference, and as it happens in this country, in Adelaide, that I talked then about a naive understanding of how do you do simulation. I had helped create for the first time a set of weather files for New Zealand, and I thought average weather files were a total waste of time, because they didn't help me to talk to students about the risk. They didn't help design. They talked about the past and the average past. So I had ideas of a hot, dry year, a cold, wet year, a whole range of other types of years that would enable us to enrich the quality of the information we produced. And it's been somewhat frustrating that it took an enormous amount of time for the design summer year to finally arrive to our consciousness, because now we're starting to provide information that building code officials might be able to use in design. Now, if, as I did in preparation for this, you start checking your assumptions, because I'm writing this as an opinion piece, I'm going to run this through ChatGPT. There are a number of times when you get this kind of slide that results from that. What is trust? We kind of expect that trust just requires us to get the data going into the model correct. It just requires that we get the dimensions right. It just requires that we use an approved weather file. But there's more to it than that. Yes, we need to communicate. There we go. But the lie that was the inspiration for the title is this notion that the performance gap is real. There is no such thing as a performance gap. Yes, I know we've measured it a lot of times. Yes, I know that our model hasn't predicted reality, but that's the nature of the model that George Box keeps reminding us of. That if we're using a model and we're comparing it to reality, we're learning what we got wrong in our simplification of reality. We need to be enriching building codes to enable people who are approving the construction of a building in that way. Now, I want to start. I was quite glad on Monday when we were told we needed to tell a story that I already had a story set up. So it's like, oh, well, I'm ticking that box. It's a bit late in the presentation, but I'm ticking the box. And the sad thing is that I think this story will be familiar to most of you. It would terrify most code officials, because I believe that they would start with George Box's all models are wrong, and my demonstration in a moment that all models are wrong, and say, well, we need to throw away the models. It's just, we need something simpler. We need, well, there are some out there, like, let's just talk about the heat loss per square metre of floor. That's all we need to do. External envelope, heat loss, there's our target. Simple manual calculation, perhaps a spreadsheet to help. Nice and trustable. It's dependable. Well, I'm not so sure. So, simple ChatGPT. What do we need to do? Well, there it is. We just need to make sure that the stakeholder has confidence because we get the same number every time. We need to be sure, if we're getting the same number every time, that they trust that the numbers are reliable, and therefore we can have very simple decision, yes, you pass, no, you don't. Job done, right? Well, I first gave a presentation to this conference in 1999 where I talked about quality assurance. After the 1993 and 1995 conferences, I reached the point where I was wanting to say to people, We don't have systems for actually being sure that we know what we're doing. We don't have systems where we're talking about the equations, we're talking about developing better and more complex models, we're talking about what George Box, I think, would call over-elaboration. But how do we know that what we've done works? So this is a contract, one of those nice things that you get every now and then in academia, to pay some research assistants to help me as the quality assurance guide to actually look at the impact in the real world of the amount of timber that's in a wall. So we've got a sketch there of our kind of construction. So for those of you who haven't been to New Zealand, it's not a lot different than the kind of construction you see around Brisbane at the moment. Pieces of timber with siding on the outside and some kind of cladding on the inside, and you put some insulation in between the pieces of timber that hold the two apart. And as specified before we did this study, that yellow highlighted part is where you calculated what is the proportion of timber in the wall. 14 to 20% of the total wall area is timber. So that's the thermal bridge that needs to be accounted for. At least at that point, I don't think Australia was. We were requiring people to do a calculation of the effect of the timber in the wall. That was specified. So the as specified number was that. And we were supposed to work that out from actually looking at real buildings and checking what the amount of timber was in the building. And we did that. We were also supposed to work out the actual effect on the heat loss of the building, and that's where things fell apart. That's where I started to panic. I'm doing the quality assurance. The easy part was we now know that in a real building, when you start to account for the fact that around a window you need some extra support to hold everything together, so you have extra pieces of timber. Every time in the three long, narrow highlights in red, you have a wall intersecting with another wall, you have lots more bits of timber that create thermal bridges. And then, in addition to that, every time you have a stair, you have something in the wall that holds the stair in place, you have hand basins that need to be held, you have baths, you have showers, all sorts of other things are an excuse for builders to go, we'll just whack a bit of timber in here and we'll be fine, right? And it bridges. And the number gets up to 46% of the wall is solid conductor from inside to outside. So we'd answered the question, the client was happy. And they were even happier when we said, well, that's the effect you really just need to know, as specified on the left, as actually built on the right. These were the effect in the houses that we looked at, the 8 different case studies. The answer they wanted, that was fine. And if you looked at as specified on the left, as built on the right, and looked at the dotted line which represents roughly this is the R value you must comply with to match the building code for the walls. It's a wavy line because the buildings were in different parts of the country. Some of those buildings, the 3 on the left, did not actually reach the minimum R value for the walls. The one in the middle was just getting there and the others were just in the safe zone. Again, the answer the client wanted. And then we go, well, okay, well, actually, let's look at the heat loss through a rough estimation of the air leakage for the building, the heat loss through the roof and the floor and the windows in addition, and still the as-built, it's a lot smaller now, as you would expect. You're going, this is basic physics, Mike, what are we doing? Well, this is looking fine. This is telling them that they can tell a story to policymakers that there are some things we need to do to improve the quality of construction in New Zealand to change building practice. Now, I need to just give you a little bit of a context before we talk about the thermal simulation results, which caused my panic. This is New Zealand using the True Size Of website to scale New Zealand at the same scale as North America on the left, Europe and North Africa in the middle, and Asia on the right. And I have inverted New Zealand because the equator in both cases for these countries is to the bottom of the map. So where the southern hemisphere, I've taken you and put you inverted so that you can kind of see the context of where we sit. The dotted line is the 45th parallel, halfway between the equator and the pole. So you again can place us as this tiny little place at the bottom of the Pacific, as the European-oriented maps typically show us. Another chip removed from the shoulder. The numbers that are there are the degree days 18.3 base for the locations that are oriented. So I hope you can, from that, from wherever you are in the world, get some rough idea of the range of climates that you might expect. I want you to remember two numbers, the 3164 for Queenstown in the blue on the top left, and the 1165 in the blue on the bottom right. They're the two towns that we did energy simulation for. Now, the other thing that you need to remember in New Zealand is we cross the 40s latitudes. And if we cross the 40s latitudes, then it's quite windy. It's called the Roaring 40s for a very good reason. We're quite good sailors because we get lots of practice at dealing with the wind. Wellington happens to be a little bit windier than most of the other parts of New Zealand. What people don't realise is the whole of New Zealand is windy. Auckland, for example, one of the examples that we're showing right now, is windier than Chicago. Much more regularly windy is the issue. So here's where things started to fall apart. As you would expect, I've created these two graphs for Auckland now and for Queenstown on the same scale. So the Auckland numbers, in terms of the heating and cooling, doesn't get really hot in international terms. Aucklanders will complain about the heat, but it's really heat and humidity that they're complaining about rather than genuine heat. Total heating and cooling amount was, as expected, adding up. But what worried me enormously is the diamonds on that graph. If building physics and physics in general is true, then a building that has, as in the as-built case, a higher amount of heat conduction between the inside and the outside, that is a lower overall R value, depending which way you want to look at it, that's what we're talking about, then those percentage differences between the as-built and the as-specified should be positive, not negative. The building with a apparently lower overall thermal integrity performed better. I'm in charge of quality assurance at this point. I'm definitely panicking. Perhaps we got the Auckland models wrong. Well, the numbers do go into the positive a little more in Queenstown when it gets colder, and it's very much a heating climate, not a cooling climate. They have the hottest temperatures in New Zealand, but they're for very short periods of time, so no one really cares. It's the cold of winter and the length of it that is the problem. We have a problem, and I'm in charge of quality assurance. So I start looking at, well, is it something to do with these buildings are typical architect design buildings in New Zealand? They've got way too much glass in any kind of rational design sense. is that the problem? We went into, because we were supposed to be doing this, have we detailed, have we calculated the thermal bridging in the right way? And then I was looking at, well, if I actually look at the kind of rational explanations, the quality of the input data, check. The geometry, check. The relevance of the weather data, well, it was somewhat common to all of them, so I'm not sure that was a problem. The material and appliance properties, yes, we've got those common between all of them. User expertise and modeling practices, well, that was my job to check. We're doing okay. The accuracy and reliability of the algorithms, well, we were relying on a tool that ASHRAE 140 had approved, so we hope we're okay. And then occupant behavior, well, that was common between all of them. So what on earth could be the problem? Possibly, we thought for a while, I've highlighted north-facing windows. North is towards the sun. You'd hope that the buildings that had less north-facing windows might have been the explanation. There was no kind of hopeful, systematic answer there. And this is when I became a fan of these graphs. This is two versions of the same graph overlaid on top of each other so we can have the as-specified and the as-built side by side, because if they were on two different pages or anywhere else, I couldn't explain the issue. For those of you who haven't seen a graph like this before, I'll take my time to explain it, because I find my students will just show it and then never explain it, and that I'm trying to emulate not doing that. But also, I apologize for anyone who's seen them before, because I'm going to, in a sense, teach you to suck eggs. And that is, 0 is the middle of this graph. Everything below the 0 line is heat flow mechanisms out of the building. Everything above that 0 line is heat flow into the building. So it should come as no surprise to the building physics people in the room that given the amount of glass that was in the buildings that you saw in the diagram previously, there's a lot of red there, representing the amount of solar gain into the building. Now that has to be balanced by something, and this calculation is looking at balancing the heat losses over a month with the heat gains over the month and giving us a picture of what is possibly happening. Now, what I want to draw your attention to, I'm not sure if I can, yes I can, is that dark brown bit. That's what we report when we report to the building code official the energy consumption of that building. That's what we buy to make a balance between two huge numbers. It's a really tiny little thing that we're... And so any error in any of the estimations of the two big things are going to show up as really big changes in that little thing in the middle. So that was kind of reassuring. We might just be looking at some noise in some way. But then I discovered that building physics is working as it should. I've highlighted with the circle and the square the bits where this graph is showing the heat loss through the opaque fabric, through the roof, the floor, and the walls. And it turns out, much to my relief, after weeks and weeks of going, I'm not sure I understand why these models don't work. The heat loss in the as-built building is bigger than the heat loss in the as-specified. Building physics is still alive. At this point, I want to return, getting away from my favorite diagram. It's the one I try to use in first year and with a class of 300 to try to get them to understand the kinds of issues that they're dealing with when they change the designs of their buildings. And that is to go back to George Box's example. I want to see a future where building code risk analysis, not building code compliance analysis, which to me is just a waste of 8,760 heat balance equations, actually inform us of the risk of things going wrong. Because my lesson out of that was, much to the annoyance of the client, that really the thermal bridging stuff was just a red herring. They needed to focus on all sorts of other things. What was clearly happening was the building was floating between our 18 degrees Celsius turn the heating on and the 26 degrees Celsius turn the cooling on, a lot more with the extra thermal bridging than it was otherwise. That was the more important lesson from that, not the importance or otherwise of the thermal bridging that they wanted us to look at. We need to recall that as we look at why is our model not matching reality, we need to recall it's a model. So how can we use the model to teach people who are in building code compliance that this is ideally following this set of rules how things work, but here is how sensitive that is to other ways in which the building might be used. I think we've dropped the ball as a community. We have identified the classic, use ChatGPT and these things will turn up all the time. Things that we need to do to make sure our model is correct. That's why we have a performance gap. It's not real. It's a construct of the way we think about what we're predicting. When to use a model to predict is just crazy. I want to also say that, again, I'm somewhat disappointed by the crowd in the room. Not by the quality of the work that you've presented, not by the excitement that I've got from going into the various sessions that I've been able to get to. It's so frustrating to have 9 different parallel sessions, but it's also great to celebrate the number of people. What is disappointing is I don't hear a lot, even now, about the performance gap in daylight simulation or the performance gap in acoustic simulation. I mean, to me, doing the background work for this, it was amazing to discover, because I've used oralizations in the past to demonstrate the effect of different qualities of finish inside a building to demonstrate what happens to reverberation time. And you can actually oralize sitting in row A, seat 1, and hearing the difference through binaural headphones, the difference between listening to someone on stage there and listening in row Z, seat 100. But the people who do that research show that if you show a picture while people are listening to the oralization, their assessment of the quality of the sound that they're listening to is different. And yet we just oralize and talk about sound transmission through walls, and we talk about sound intelligibility inside a space in acoustic terms alone. So my question to my fellow conspirators in what I consider the priesthood that is building simulationists is, shouldn't we, as simulation experts, be advising building code writers that building performance simulation should be a means of evaluating the risk of a building, not just the performance, but something more than that? Otherwise, why are we doing these 8,760 calculations? We're modeling what architects would call a sketch. So we're doing what's on the left, not what's on the right. Architects are used to doing this all the time, but we talk to them and building code officials expect that we're talking about the thing that's on the right. Our model isn't that good. I want to also, with the few minutes that I have left, just point out a couple of lessons that I've learnt from different students over time. Herman Molina talked deliberately to people about comfort. And we made sure that we weren't talking to engineers who had been brainwashed to think about comfort, in particular thermocomfort, but lighting or acoustic comfort, because he talked about all of these. And we weren't talking to architects who had been similarly brainwashed into what that might mean. And he came up with his concept of the feeling of comfort, and the last paragraph talks about some of the implications of thinking just about the temperature, not about how people might open the windows and what might else affect their opening of the windows. But he pointed out something to me that we toned down in the thesis, but I don't want to tone it down at this point. He pointed out that when people write textbooks about comfort, and it doesn't matter whether they're talking about acoustic, lighting, or thermal comfort, they start off with this grand statement. It's a complex combination of the mind and the body. And then almost in the next sentence, they go, well, we're just going to focus on the body. And that's what we do. We model, typically, the impact of temperature on people. It's not really enough. I've, of course, involved myself in various exercises. I was involved in the early days of, I need to get this right, CIE TC 3.33, which is the lighting equivalent of ASHRAE 140. I was able to get Autodesk to sponsor a master's, which I thought was extraordinary at the time, which is why 3D Studio Max appears as one of the things that we were demonstrating complies with their version for lighting of the best test. Fine. We all have that kind of fascination. But I have to keep reminding myself of James Sullivan's PhD. It's one of the most eloquent, to me, beginning paragraphs of a PhD that I've ever had the pleasure to supervise. But he pointed out good performance, and he reminded me that our definition of good performance is quite limited. And this is the most spectacular example I've ever come across. Pretty much everyone in the room is from a country where 300 to 400 lux is what we aim for as good lighting. We're making the assumption that good lighting is to ensure we're given enough light to see clearly and carry out our desired tasks. It's a nonsense. If you actually look at the literature in the field, to read a normal piece of paper, white piece of paper with black text, we need somewhere between 20 and 50 lux if we've got normal eyesight. I'm struggling these days, but normal eyesight, we're fine. If it's 6-point type, it's been demonstrated we need 100 lux. So where's the other 3 times that coming from? It's coming from people who don't like to sit in that level of darkness for a start off. They want brighter spaces, so they're prepared to pay for it. The standard is not about doing a task, the standard is about something else. And yet the standard is written as, let's have this light level on a desktop. That's not what people want the 300 lux for. They want the walls to be reasonably bright when they look at them. They want the contrast between the windows outside and inside to be reasonable. We're not writing building code. We can simulate it, but we're not writing building code that has the richness of this kind of diagram, and we ought to be. That's my challenge to us. I'm not challenging just you, I'm challenging myself at this point. Of course, if we're communicating as effectively as possible. What we have on the left is, again, essentially ChatGPT, my sensible analysis of what we need to do to report well. I had the pleasure of supervising, she's there, Elzine, in her Masters, where she was looking at, can we do performance sketching? And so she created a workshop which she would walk a group of engineers through and a group of architects through. And she did it using Ladybug tools. And in 2008, she was super excited about how I should change the whole of my teaching because this tool would change my future forever. Or about 15 years later, I discovered she might be right. But at the time, I was terrified by those visual programming language wire diagrams, which just were horrendous. I could agree with her that the graphics were tremendous. And the engineers and architects agreed. I'll let you read their responses. The engineers, of course, were saying, there's this thing called Sapphira. Please don't encourage architects to use it because we don't trust it and it doesn't agree with any of our models. And then the architects were saying with the script that she'd created, this is great, but can you make it simpler? And the engineers were saying, this is great, but can we have more ability to get underneath to change things and understand what's happening? And her conclusion from that after the workshops was, actually what we need to have, and what I believe we need to then start feeding from that process into building code compliance that is richer than we currently have, is, and this came up in the education discussion yesterday, the engineers are the people who know and distrust the model and can therefore interpret it well. But the architects are designing and making the decisions. And at the moment, we have this, here, can you make my building work kind of problem rather than a collaboration. Her proposal, which I see people starting to use now in some of the documentation of the Ladybug tool that she was using, was that if you could get the engineer and the architect into the room at the same time, big if, I understand, then what you would do is get the discussion on what are we going to actually explore as a design team, and the engineer would build the model that the architect would use. So you don't have the translation problem, you just have, here, use this to explore the concept. We trust its output, you can trust its output, and when that is not good enough, then come back to us and we'll elaborate it in the ways that you want to explore next. It's a collaboration, but how do we build a building code that enables that collaboration? My thesis in this presentation, my proposal is that we need performance indices that test real-world scenarios. Not ideally, here's a performance single number, but ideally, here's a building performance single number, and here's how it could go wrong. We need to engage in a discussion with building code officials to start to ask questions because we know where it goes wrong. We've been studying the performance gap for quite a long time now. We know the kinds of scenarios they should be building into building codes to say, that's the ideal, it kind of ticks that box, but the risk of it going wrong is this. If you take that building and make it into an apartment when it was designed as an office, which is, I'm sure, happening all around the world, it's certainly all over Wellington at the moment, these are the likely implications. Do you want to build that into your thinking at the start? A building that actually might adapt to the future rather than require lots of work, then you need a richer building code than we currently have. With a very short time left, I just wanted to point out that there have been attempts to build targets that we might believe in. I was quite attracted for a while by Charles Ely. His colleague is here somewhere, Eric. Anyway, yeah, there we go. Had a proposal at the beginning of this decade, no, we're even beyond that. 2011 is that long ago, that we actually defined best not in terms of 20% better than code, 20% better than some kind of prescriptive minimum. We set net zero as an absolute target. That will never change, was the proposal. I already realized that, of course, with regenerative design, it has changed. Net zero is no longer enough. We want to actually be contributing back to the grid. We want to be improving the environment. So possibly that kind of target is a daydream. We definitely want to have a building code compliance process which talks about being grid friendly, that starts to use the 8,760 calculations properly. So we are identifying, we've put PV on the roof, and no, we're not going to be selling it back to the grid when the grid is already generating enough electricity with its own PV. We've got something that actually works with the way the program ought to work. And the reason I was looking for the history of neighbours is because I was somewhat attracted by the notion that targets might be set by a neighbours type process. I think we should be exploring that, but again, exploring how neighbours goes wrong, or what we can learn from buildings that don't work. I want to finish with, Joel, you're right here. Ron Judkoff's colleague, similar kind of experience in terms of developing best tests that became ASHRAE 140. We know that the difference between tools was being identified in 1985 as a problem. So we've developed a process by which we say, well, let's trust the fact that if I use tool A or tool B, and it's been certified according to a best test, ASHRAE 140 kind of process, the numbers might be different. We know same user, different tool, different user, same tool, they all produce differences in the absolute numbers, but the relative differences will be the same. So tool A and tool B can be trusted to produce the same recommendations in terms of design. When I was preparing this, one of the things that I did a literature search for was, well, how many people have actually tested that concept? And it turns out to be a disappointingly small number that I could find. I would love to find more, because suddenly I got nervous about that assumption. So I want to zip past the conventional approaches. Yes, we can do all of these things, and we should be doing all of the things. But I want to finish with what I believe is a first draft on the way we should start to think about discussions with building code officials. That is, we want measures of performance that relate to reasonable expectations of users' perceptions and desires. The lighting issue, the feeling of comfort issue. We want definitions of acoustic comfort that relate to how noisy it is outside, how well the facade will work if you open the windows, and what will that do to your thermal comfort if you're taking those kinds of things into account. Let's not design openable windows next to a motorway that has a rush hour in the late afternoon. Let's look at the whole building and what people want inside the building. We want definitions of light comfort that relate to the kinds of things that Jamie was talking about in his... Oh, can I do that? Oh, that isn't quite what I wanted to do. There we go. I can scroll the text to make sure I'm not missing something. Definitions of thermal comfort that relate as much to time of day and activity as they do to annual energy use. We should not be assuming, as I think our building codes currently do, that if we get the energy right, people are going to be thermally comfortable inside our buildings. It's just crazy. So we want a mode of standard operation that is the tick, but then a range of scenarios to test by that enable us to use the richness of the 8,760 calculations that we do for thermal design and the 4,000 we do for daylight and so on, the stochastic approaches that we do to for acoustics. Because he tangata, he tangata, he tangata. There is a Whakatoki or Maori proverb which asks, what is the most important thing? And he tangata is the people. The people. The people. Thank you. Now, Quentin suggested that we were starting early. Did I mind starting early and just having lots of time for questions? So I don't mind if you walk out. I'm kind of used to that. I lecture at a university, so at times people have other things they want to do. I have, typically, it's not my classes, but I have had problems in recent weeks where I realized there's another lecture immediately after my tutorial, and there's a bunch of students sitting around still working on my tutorial. I'm going, there's another lecture. In fact, I'm going to it because my fourth year students really want to hear this innovative presentation of BIM in the construction course. Oh, yeah. Okay, so I'm used to that. So if you want to leave, do leave. But what I'm really interested in is getting feedback, because this was deliberately me saying, are there microphones, or do you want us to just shout it out? Because I'm aware that we're online, and I've no idea what people are looking at online. But to me, other suggestions about what we should do or how impossible this daydream is, I propose quality assurance should be improved in 1999, and I sat through PC's presentation yesterday thinking, oh, we've reached there. So that's 26 years. I'm not necessarily expecting we have an answer by tomorrow, but Joel, yes. There's a microphone coming to you. There you go.
Check. Okay. So great. Thanks for calling me out there. So I just wanted to make a comment about the useful models and be encouraging. And so, when we do a base case or a reference building, that's where we expect, greater differences among models. And really the strength of our models is when we look at sensitivities. So we lay things out, but it's the sensitivity aspect, whether you're looking at window types or shading or HVAC systems, that's where we tend to see the better agreement in things like the best test. Right. And so I just wanted to make that point.
Oh, no, that gives me reassurance that if we're looking for tigers, we're going to find them. That is really, really hopeful. Yes, another in the back.
Thank you so much for the keynote speaker. I'm really excited that we actually have a good look at how we do energy modeling. One thing that I realized is that when we look at the building code and the use of simulation for building codes, one side simulation was used to generate the DIM to satisfy requirement of the building codes, which probably should be done by an expert. But then there is this, I'm really excited about you say about the building code. Once something is really too complex, it's actually shown mediocrity. Like what we are trying to say is that to have a very simple, good to understand performance requirement in the building codes without too much of a headache trying to read, trying to understand what the building code is trying to do, which is a problem that we have here in Australia for some part of the building code. Now, what do you think about a building code that's trying to make people use simulation more? Because especially like in Australia, our building code actually try to mandate operational target in the building code. Because when we have a DIM to satisfy requirement, they are saying that this is your wall, your R value have to be this DIM compliant, but probably in the actual, you might have uninsulated areas, that the actual performance that the modelers that made and then determine the R value when they set up the building code is not going to actually give the performance that we have in real life. But if we have energy simulation as a way to achieve compliance, but we set the requirement as operational performance, like when neighbors trying to get to the J1V1, like you have to achieve a 5.5-star neighbors rating in an office building. But that is really hard being taken up by the industry because of there's a lot of requirement needed because you model for operational performance. You're estimating an absolute figure. While if you're doing like the other pathway, J1V3, you actually set up, okay, based on this deemed to satisfy requirement, my energy budget, my reference building is this. So you're doing a comparative analysis. But your propose is not really going to be a real life. It's just a comparative, like, okay, I'm trying not to be as bad. I'm probably a bit better than my energy budget. But that doesn't tell you how's your real life going to be. But what do you think about having the building code based on operational performance as the way forward? Thank you.
Wow. So I'm going to start with, I'm a great believer that simplification of the calculation method literally destroys the usability and the likelihood of improvement of performance, that we need to enrich the way we do calculations. I also am struck by the neighbours' compliance contract approach of actually having independent verifiers of models. I think that is hugely complex and probably only justifiable for very large buildings, but is a starting point. In relation to how should we then verify that a building complies, I worry immensely. And actually, I'm going to apologize to Quentin and Nikki and Patrick, because I'm pretty sure I've used this for the last 40 years in talking to people. The certification of the performance of a building, to me, is like the number that you get when you buy a car that tells you its fuel rating. You know that when you get into that car, your driving style is going to be different. So the notion that you get into a house or you get into an office building and it will perform to the standard that was originally calculated, to me, is the biggest problem that is creating the performance gap. Because we're trying to build buildings that might be an office building this week and might be an apartment in 20 years' time, because it's faded or that part of town has moved on to somewhere else, and now we could, if we wanted to waste resources, completely pull the building down, and we could adapt and reuse it. So I worry about the prediction notion. That was the core of what I was talking about. I do like energy performance certificates that actually keep people honest and help people to understand how to improve the operation of their building, but that's different from a building code. That's something beyond that, the neighbours rating processes that we have at the moment. It is complex. I want to enrich the understanding of building code officials as to how to get better buildings and what is the risk of the building being misused or used differently than it was modelled. But I can't see how you would factor into that making someone accountable in the building for the way they're currently occupying the building. I cut my teeth. My first research project was looking at the energy performance of all the central business district buildings in Wellington City, collecting all of the energy data for it. At those days, yes, grey hair, it was those days, I could walk down to the single electricity supplier for Wellington City and say, there's the geographical boundaries. I want all the energy records for all the businesses in that boundary. And they'd go, here. I didn't have to write to anyone to get their permission to look at their records. I just walked away with them. Now, what was interesting is the oil and gas companies who provided the heating oil and the gas company did the same thing. And what I learnt from all of that process was there was very little relationship between the energy use in the buildings and the fabric of the buildings at all. It was all to do with the way people were using the buildings. We did correlations of the window sizes and the age of the building and the height of the building and a whole range of other properties. And what we learnt was the deterministic equations weren't relating to how people were using the buildings. We did a few case studies where we went into those buildings, and this is a lawyer's office. So one person, it seemed like every 100 square meters. It might have been every 30 square meters. And then we went into a banking behind the scenes, not the front of house. And it was like, well, you were lucky if it was one person for every 10. It was more likely one for every 7 these days. That difference in ostensibly the same office building on 2 different floors in the office building is going to make a huge difference to the actual energy use. So I like the process that Neighbours is going through to making people responsible for managing their own day-to-day energy use, but I'm not sure I can see a connection. I like the concept of the connection, but I'm not sure I can see a connection between what you do with the building code and making people accountable for how they're using the building down the track. Yes. So. As long as it's quick. Yes. PC. I write a reply. Yes.
Well, I think I should do a couple of quick comments. Number one. Thank you. So number one, as the independent design reviewer on these things, all I'm doing is I'm not really interrogating his modeling skills. I'm saying, okay, this is the design that's documented. Mm-hmm. This is the model that you built, and the output from the models look reasonable for office buildings because we've got 20 years worth of history.
Right.
So I'd leave that one there. The second thing I do want to say is that we do account for the usage of the building. If you want to learn more, please come to the neighbors session this afternoon, but we do. Mm-hmm. The third thing is probably because, generally offices work from 9 to 6. Maybe if you've got a few slaves, maybe it might go a bit longer. But generally, that's kind of accounted for within the neighbors equations. It is probably also the reason that neighbors is not getting as many ratings in other sectors of the building because it is money, money, money.
Right, okay.
Thanks, Mike. Really appreciate it.